Hello, hi. My name is Parasar, and I am a PhD student at ISC in physics. So this is the second week of the PMRF TA sessions. Uh, so uh, let me share the problem screen. All right. So this week we have some problems on the formalism of thermodynamics, as in, to be more specific, on the fundamental equation, and how to derive various quantities from the fundamental equation. Uh, so yeah, let's start with this problem, the first problem. Uh, so in this question, we have to uh, uh, find which one of these given equations is not physically allowed to be a fundamental equation of thermodynamic system. So by the way, most of the problems that we'll be discussing today are from this textbook uh, by Callan. So I have indicated the problem numbers beside the question, so you can feel free to refer to these problems in the textbook itself. So yeah, again, like just to emphasize, these are not designed by me. These are from this textbook. Uh, anyway, so now going into the question, we have to find which of these five given relations is physically okay, and which of these is not okay. So here, and in this entire set of problems that we are going to discuss today, S, U, V and N are they stand for the usual notation. So S is entropy, U is the total energy, V is the volume, and N is the number of particles. Uh, so uh, so when we have an equation like this, S given as a function of U, V and N, this is called uh, a fundamental equation of the thermodynamic system, because uh, every thermodynamic property of the system may be derived from this. Uh, if we know this fundamental equation, then like I said, any property that may be desired can be calculated or known from this fundamental relation or equation. This can also be inverted to write the internal energy U as a function of S, V and N. So both of these can be given. It is like it is sufficient to give one of these, then the other can be derived. So that was just a quick recap. Uh, anyway, so now the most important property of this function, this entropy function, or the uh, uh, or the fundamental equation, is that uh, uh, this entropy is extensive. Uh, or more precisely, if we want to write this as an equation, if we scale the system by a size lambda, So lambda could be any positive real number. Then the entropy also scales by the same number lambda. So U, V and N are all extensive. The energy, volume and the number of particles in system are all extensive. So if you scale the system, all of those would be scaled by lambda, and the entropy would also be scaled by the same factor lambda. So an equation of this form is called a homogeneous equation. So in this case with degree 1. Yeah. So now coming to the second property, it is the property that the entropy has to be monotonic in U. It should be earning non-decreasing function of U. So the idea is that if you put more energy into the system, the entropy of the system should increase. So or this is equivalent to saying that the temperature is positive. Yeah. Although there are of course systems where this can be violated. For our purposes, let's say that our entropy function has to satisfy this. Only then we call it physical. For this purpose, I mean, for our purpose. Yeah. So that was the second property, and what you could also demand is that the entropy is 0 when T is 0, or dou U by dou S is 0. Yeah, this is like the third law of thermodynamics. So now our job is to look at these given these equations and figure out which of these equations may violate one or more of these postulates, or the basic properties that have to be satisfied by the entropy function. Okay, so all right. Okay, so let's go through these things one by one. So the first in the first one we have S is proportional to NVU all to the 1 by 3. So now clearly if you replace N with lambda N, V with lambda V and U with lambda U, then S will go to lambda S. So it does indeed scale correctly. So it does satisfy the first property that we want. That's a check. That's a tick. And similarly, we can ask whether it is monotonic or not, whether it is increasing or not. So clearly, S goes as a positive power of U. So dou S by dou U is obviously positive. So as U increases, S increases. So that's fine. And similarly, when t is 0, so that means in this case uh, u is 0, because t goes as t is dou u by dou s, or that is the reciprocal of dou s by dou u. I mean, these are evaluated at constant volume and number of particles. Yeah, so this goes as u to the 2 by 3. So clearly if t is 0, u is 0, and when u is 0, s is entropy is also 0. So that's fine. So when the temperature is 0, the entropy is 0. So this is a tick on all three conditions. So this is indeed a physically valid uh, fundamental equation, which gives rise to a well-defined thermodynamic system. Okay, all right. So similarly, uh, let's try to look at the other ones. Okay, uh, so we are now the second. We're not doing the second one. Now we see that even in the first condition we have some problem. So if you scale the system by lambda, then this is going to be scaled as lambda to the power 2/3, which is bad. So this is not extensive. So it does not satisfy the first condition that we wrote down. Yeah, so this is not a physically valid equation of state. Yeah, now let's look at the third one. So here it is, s is let me go back and check this again. Yeah, some constant times nu plus beta v square. So checking for extensivity, uh, so under this scaling, s goes as square root lambda square times s, which is lambda s. So this is this is fine. All right, and now coming to the second point, the second condition. So s goes as square root of u plus something. So clearly it is an increasing function of u. So dou s by dou u is positive. That's fine. And yeah, so it can also be checked that when the temperature is 0, uh, the entropy is indeed 0. So this is a tick on this front as well. So yeah, so this is a valid equation. All right, so let me check if okay. Uh, So this time S is alpha v cube by nu. So this is going to be actually the correct scaling, or it is extensive. This is fine, but notice that S goes as 1 over u. So S is in fact a decreasing function of u. So yeah, so this is not allowed. So already we can see it is not a uh, it's not a valid equation. Yeah, finally, if we consider the final question, so it is yes. So the exponents of n, v, and u add up to 5, and there's a 1 over 5 uh, exponent. So clearly, uh, it is extensive. The entropy is extensive. All right, and also it is an increasing function of u. And similarly, we can see that when temperature is 0, that means u is 0. So that means S is also 0. Yeah, all right. So uh, this is a valid physically uh, 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 it's a it's a physically valid fundamental equation. All right. Uh, so to summarize, in this question we have looked at uh, various equations which could be fundamentals which could be fundamental equations of a thermodynamic system, uh, and found out which ones are not allowed based on the postulates that S is extensive, and it should have the scaling, and it's a monotonic function of u. And and that when the temperature is 0, the entropy must be 0. All right, that's about the first question. Okay. Yeah, so now let's move on to the second question. So in this problem uh, we have two subsystems in a combined system. So this combined system is isolated, and so this combined system has uh, two partitions A and B. Two systems A and B make up this full combined system. So it is basically the same material or the same thermodynamic system in both these partitions. So they are described by the same fundamental equation that has been given, and there is a wall or a membrane which separates these two partitions. I mean, there's a wall which separates these two systems, and the volume and the number of particles of each of these subsystems has been given. All right, and so initially this wall that's given to be a rigid, uh, it's a rigid adiabatic and impermeable wall. So uh, because it is rigid, uh, the wall cannot move, so the volumes of each of these uh, subsystems is fixed, so volume cannot change. uh, the volumes of both the subsystems is fixed, both A and B is fixed, and when it is adiabatic, that means heat cannot flow between these two subsystems, or heat can't be exchanged. And finally, this means that particles cannot flow from one part of the system to the other part, or from A to B. Particles cannot escape from A to B or B to A. So particle numbers of each is fixed. So this is what we have initially, and at some point the wall is now made diathermal. So that means heat can now be exchanged between, sorry, yeah, sorry, yeah, so now the heat can now be transferred or flow between A and B. So this wall is made diathermal. So now this is done, uh, obviously the volumes and the number of particles of each of these subsystems is still fixed. It does not change because the wall is still rigid and non-porous. So Na, Va and Nb, Vb, they are all fixed. But because of this change, because of making uh, this wall to be a diathermal wall, uh, heat can now exchange between these two systems, and as a result, the oops, the uh, the uh, the energies of the the individual systems energies can change. So there is a certain freedom uh, for this full system, in that it will explore all possible states uh, with different energy distributions for systems A and B, and uh, there is a particular configuration, or there is a particular distribution of these two energies UA and UB among the two subsystems, so that finally the system is at equilibrium. Of course, the sum of the energies UA and UB is that is the total energy initially in the system, that cannot change because this full system is isolated. Uh, so now the question is, what is the distribution of energies among A and B? That is what we have to find uh, at equilibrium. All right, so this is a classical uh, problem in thermodynamics, and the you can say one of the postulates uh, of the uh, thermodynamics is that the equilibrium state is achieved for the configuration which maximizes the entropy among all these allowed configurations, which maximizes the entropy, uh, the total entropy of the system. Okay, so uh, uh, let us be more concrete and write an equation for this. So let's say the distribution is UA and U minus UA between A and B, and then the total entropy would be uh, so this is the total entropy, and this entropy that we want to write, this is the entropy if this this is the entropy if this particular distribution of energies takes place. So this is a function of UA. This is a function of how we distribute the energy, and this is SA of UA and ABA. Oh, okay, I think the order, I messed up the order. Yeah, UA plus SB of U minus UA VB comma NB. Okay, so we know the fundamental equation for each of these subsystems. In fact, it is the same, and so note that in this postulate, the total entropy is the sum of the individual entropies of the individual systems if it were at equilibrium with that distribution. So note that we are doing all this to find the uh, to, to, to find the values of UA and UB at equilibrium, but uh, obviously this is not an equilibrium for any general UA and UB, but the statement is that let's assume there is a particular distribution and if each of the individual parts of the system is at equilibrium with this particular distribution, what is the entropy? And we have to maximize the entropy over this distribution by uh, yeah, I mean, sorry, we have to maximize this entropy, uh, uh, which is the sum of entropies of the individual systems uh, for a particular distribution, if all those systems were at equilibrium with respect to the distribution. Okay, maybe that's a lot of words. Okay, uh, let me uh, make this clear by writing that we have to maximize S total of UA with respect to UA. And each of these quantities that we wrote, those are the those would be the entropies if so for example, this first term, that would be the entropy of system A if it were at equilibrium with energy UA. So once we form this total entropy by adding all these, we have to maximize, like I said, the this entropy with respect to the distribution. So in this case, we have only one variable to vary, which is the energy of the system A. Then the energy of the system B would be automatically fixed. Yeah. So to find UA at equilibrium. Yeah. Let me check if there was something here. Yeah. All right. Yes. So this is now going to be A times NAVA whole to the 1 by 3 plus NBVB U minus UA whole to the 1 by 3. So now so here all these are just constants, NA, VA, NB, VB, these are all constants because like we discussed, the wall is still rigid and non-porous or impermeable. So UA is the only variable with respect to which we have to maximize this. So clearly it has yeah, let's see. So this is a okay, this is a function which looks like this, something like a to the sorry, a times x to the 1/3 plus b times one minus x whole to the 1/3. So x here is UA by yeah, it's UA by UA by U. So we can get it to this form by dividing this thing with I mean dividing the entropy with, so S total by u to the 1/3 is going to be a times NAVA times UA by U whole to the 1/3 plus plus NBVB 1 minus UA by U whole to the 1/3. So A is just a positive constant, so it does not affect maximizing this function. Similarly, U is a positive U is a positive constant. So finally we can write this as a times x to the 1/3 plus, sorry, there is a, yeah, there is obviously a 1/3 here as well, and here. Oops, sorry. B times, where a is going to be NAVA whole to the 1/3 and B is going to be NBVB to the 1/3. Yeah, that looks all right. So basically we have to maximize this function with respect to x between 0 and 1, sorry. Okay, all right. So that would involve finding the stationary points of this function. So let's quickly do that. Yeah, so that means that yeah, so this can be solved for x. So a by b, the 3 by 2 is going to be x by 1 minus x. So x is going to be yeah, x is going to be a by b whole to the 3 by 2 by, obviously, yeah, 1 plus a by b whole to the 3 by 2. Yeah, so this is what we want. So UA by U is this is a fraction of energy in the system A, in the subsystem A. So this is going to be square root of NAVA by NBVB by sorry, um, so obviously if both the systems are identical, if NA is equal to NB and if VA is equal to VB, then obviously we would intuitively expect that that the energy would be equally shared, and indeed so we see that from here. So anyway, so this is what we wanted, the fraction of energy shared by system A. Oh sorry, okay. All right, let's go to the next question. So we are now at the third question. uh, in this question, the fundamental equation of the system is given. It's been given to us, and we have to find the equations of state. So that means we have to find the temperature, pressure, etc. Okay, so let me just write whatever is already there. I mean, okay, and we have to find the equations of state. So we can make use of the definitions of the temperature, pressure, and so on. So U is a function of S, V, and N. Let us write uh, it like this. So then du would be TdS minus PdV plus mu dN. So the temperature is it is the derivative of U with respect to x at constant V and N, and similarly and mu is dou U by dou N at constant S and V. So we could just simply define the temperature, pressure, and chemical potential like this, starting from the equation of state, and starting from the equation of state, we could define these derivatives, these partial derivatives that we have from the equation of state as temperature, pressure, and chemical potential. And indeed, it turns out that these definitions are naturally meaningful, and they give rise to the notion of temperature and pressure that we are otherwise familiar with. Anyway, so in this question we just have to make use of these equations. So these are the three equations of state. So the temperature is this, and the pressure, uh, so the pressure has this negative sign because we want it to be positive, so this definition includes the negative sign. uh, so the pressure would be A is cubed by NV square, and finally mu is going to be minus A s cubed by n square V, or this is minus 1 over n times A s cubed by V. So A s cubed by yeah, sorry, there's another n here, which is minus U by n. So this is the internal energy per particle in this case. So it is minus U, minus little u. So little u is the internal energy per particle. So similarly, we could also write P in terms of U. So it would be U by V. So the pressure in this case is exactly equal to the internal energy density if the equation of state is like this. Yeah, so yeah, so in this question we just made use of the uh, definitions of the temperature, pressure, and chemical potential, and used the equation of state given to find. I mean, sorry, we used the fundamental equation given to find the equation of state. All right, so now again we have a similar question. So the equation of state is given, and we have to find. I'm sorry. The fundamental equation is given, and we have to find the equations of state. So these little u's are intensive quantities. These are per particle quantities. So U is internal energy per particle, and S is I mean the little s is entropy per particle. The little u was internal energy per particle, and V is volume per particle. So it is the volume occupied on average per particle or by a particle. Yeah, so we could simply write this in terms of the familiar uh, uh, equation of state in terms of the capital U's, the extensive quantities. So u is alpha s squared by n minus beta v squared by n. So just taking these partial derivatives, I'm doing nothing more fancy. So this is 2 alpha s by n. So it'll be 2, it'll be 2 beta v by n, and chemical potential is minus 1 over n square times alpha s square minus beta v square, which is simply I mean, we can also write this in terms of the energy per particle, just like the previous case. So this is going to be minus u by n, or it is just little u, minus of little u. Yeah, so these couple of questions are just to make us use the definitions. So right now I want to pause and try to stress that. So like in all these examples we are seeing, once we know the fundamental equation, we can calculate all the equations of state that we want, like the relation between various of those quantities can be further determined from the equations of state, uh, uh, and we'll see examples of that in the next coming problems. So yeah, now if we go to this fifth question. So this is again the fundamental equation given for a system, and now it is given that some particular process is done on the system, uh, or the system undergoes some process, and we have to find uh, how the temperature changes when the system is expanded at a constant entropy. So first of all, let us uh, try to write down the equations of state which involve temperature and pressure. So then we could see uh, how the temperature and pressure change in a particular process. So first of all, without delay, let us do that. So this is little s. Yeah, this is just some constant k. So in terms of the extensive variables, it looks like this. Sorry, my u's and v's are looking very similar. Sorry about that. So so this is going to be n square by v square times exponential of s by nk, or we could say u is a n by v square exponential of S by Nk. Let us now find the temperature and pressure, because uh, what we are given is the change in the pressure, uh, or that the pressure is halved in this process, and we have to find how the temperature changes. Uh, so maybe we can try to get a relation between how pressure and temperature are related in this process. So let's first try to find the temperature. So this is going to be dou u by dou s. So we have to take a derivative with respect to s. So this is going to be a by v square k times exponential of s by nk. Or we can write tv square is going to be a by k times exponential of s by nk. Yeah, so now note that this process that has been described in the question, that is that's an isentropic process. It's an isentropic process, or a process where the entropy remains constant. So s is a constant. So in this process s is a constant. So tv square in this process is a constant. Okay, uh, so similarly, let us try to find such a relation for the pressure. So pressure is minus dou u by dou v. So that is going to be 2an by v cube times. So again, s is a constant in this process, and the number of particles is also of course constant. We're not changing the number of particles. So pv cube is a constant in this process. So these are the two relations we have obtained for this process. So of course volume also does indeed change in this process, but what we want is the change in the temperature, given that the pressure is halved. So we need to find some relation between pressure and temperature. So that is that can be done by getting rid of v in these sort of equations. So we can see that p square, yeah, so p square by t cube is a constant. If you square the first equation and divide it with the second equation, we come to this conclusion that p square by t cube is indeed a constant in a isentropic process. So it is given that uh, p is halved, so p goes to p by 2, or let me write p final is p naught by 2. So t final is going to be Yeah, okay. uh, yeah, so yeah, T final cube by P final square is going to be T naught cube by P naught cube. So T final is going to be T naught times, oh sorry, this is square here. Yeah, so this is going to be T naught by 2 to the 2 by 3. So in the previous couple of questions we just found the equation of state for for the given system from the knowledge of the fundamental equation. So in this case we just went a step further and used these equations of state to, for example, say something about how the temperature changes in some particular process. Yeah, so this is just to show how the equations of state can be can be applied to say how various quantities change in various processes. Okay, so all right, and let's get to the next question. So the idea of this question, the sixth question, is that these intensive quantities Tp and mu that we defined, they are not all independent actually. These are not all independent. So only two of them are independent. So what we mean is that, so these are all functions of uh, S, V and N, let's say, and these functions uh, are not independent. We can find the function uh, mu S, V, N from knowing these two, let's say TSVN and PSVN. So if these are known, we can find this function. That is the statement. Uh, let us look at this example first, and we'll discuss this in more formal, or discuss or like revise this concept in a more formal way. Uh, so this example is to show that uh, 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 that relations between TP and mu can be calculated, uh, and that these are not all independent. So U is alpha s to the 4 by nv square, and so T is going to be 4 alpha s cube by nv square, and P is going to be 2 alpha s to the 4 by nv cube, and finally mu is so we have to uh, eliminate SV and N among these three equations if possible, and find a relation between oh, the screen is not getting updated, I guess. Yeah, just a moment. Sorry. Sorry, just a minute. uh, yes, yeah, sorry, it is back now. So we have to find a relation between TP and mu by eliminating S and V, SV and N from these equations. So it is yes, okay. So we can see that if you take P by T, so that is going to be 1 by 2 S by V, and similarly we can right, so we need, so we can write this as minus alpha S by N whole square times sorry, yeah, S by N whole square times S by V whole square. So we have S by V is 2P by T, and what about S by N? Yeah, so we can get rid of V from this equation, from these two equations actually. So let us do yes, so T cube by P square. So we are doing this particular combination, this particular ratio, so that we can eliminate V from this and get a ratio of S by N. That's it. So T cube by P square is going to be 4 alpha whole cube S to the 9 by N cube B to the 6 divided by 2 alpha whole square S to the 8 divided by N square B to the 6. So finally this is going to be 16 alpha S by N or S by N is going to be 1 by 16 alpha T cube by P square. So now we can express the chemical potential solely in terms of P and T because of this relation. So mu is minus alpha times S by N whole square times S by V whole square. So it is 16, sorry. Yeah, 1 by 16 alpha T cube by P square whole square times 2P by T whole square. So it is finally once we take care of all the numerical factors, it's going to be minus 1 over 64 alpha, I think. Yeah, minus 1 over 64 alpha T to the 4 by P square. Yeah, so finally we have expressed the chemical potential only in terms of temperature and pressure, or this is a relation between only chemical potential, temperature and pressure. So all these three are not independent, so only two are independent, only two among T, P, mu are independent. Yeah, so this is so what we have discussed just now, that is an example of this what is called the Gibbs-Duhem relation. So the fact that all these three intensive quantities T, P and mu, they are not all independent, can be expressed in terms of uh, equation satisfied by these three quantities, which says that all these three are not independent. So let us just a minute. Yeah, so let us discuss this Gibbs-Duhem relation in general. Just revise this this concept for a general system. So this actually stems from the postulate or the basic property that all these energy and entropy are extensive quantities. So let's say you have internal energy as a function of S, V and N. So it satisfies this crucial property that like we discussed at the start of the session, if you scale the system by a size lambda, then the internal energy will also be scaled by this same factor. So like we discussed, this is a homogeneous equation of first order, of first degree. So it can be easily shown that for this sort of a system, so we have a function of, let's say here 3 variables, and this function is or let me say it's a homogeneous function. Yeah, sorry, it's a homogeneous function. So we have we have a homogeneous function of degree 1, and the the function then can be written as so this is at constant b and n. So we can write this as sum over the partial derivatives of this function multiplied by the variable itself. So of course, let me be more clear and precise. So this is of course still a function of s, v and n plus dou u by dou v times v plus dou u by dou u by dou n times mu. Sorry, dou u by dou n times n. Alright, so now from the definitions that we had, this is going to be temperature. This first partial derivative, that's nothing but the temperature. This is nothing but the pressure, or indeed the negative of pressure, and this is the chemical potential. So these again are at constant n and s. This is when the other are kept constant, so s and v are constant. Yeah, so we have an equation of this kind, which expresses sorry the internal energy like this. This is called an Euler relation. So once we have this, we can calculate its differential. But we also obviously have this, which says du is TdS minus PdV plus mu dn, because these are the derivatives of, for example, t is the partial derivative of u with respect to s, and so on. So we can always write this differential. So because of this, we can see that like these terms will cancel, and finally we get a relation like this. So this is the Gibbs-Duhem relation. I hope I'm pronouncing it right. Okay, let me just like that. Yeah, this is the Gibbs-Duhem relation. So this is like a differential equation that relates Tp and mu, or Tp and mu will have to satisfy this sort of an equation for any system, whatever be the equation of whatever be the fundamental equation, whatever be the thermodynamic system, the intensive quantities will have to be related like this, or in this case there are only two independent variables. So what we saw in the previous problem is an example of this. So in this case we could just simply find the relation between Pt and mu by getting rid of the other variables. But in general, one could integrate this equation, for example, to find mu into if we know the functions p and t. So in principle one could integrate this to find, let's say, the third equation of state, like mu, once p and t, the functions p and t are known. Okay, so yeah, this is yeah, just a recap of that. And what we saw in this previous problem is, like I said, it's a simple example where we actually calculate this relation, find this relation. All right. Okay, so in this case, it's actually like the reverse of what we have been doing. So in the previous questions, the fundamental equation has been given to us, and we have been finding the equations of state. But in this question, certain equations of state are given, and we have to find what the fundamental relation is. Yeah, we have to find what the fundamental equation of the system is. So notice that we have been given two relations. So now the question actually arises: is this sufficient? Is this sufficient to find everything about this thermodynamic system? Or in simply, is this sufficient to find the fundamental equation of the system? So the discussion that we had just before this, uh, that will actually tell us that indeed it is sufficient to have this relation. I mean, it is sufficient to uh, have these two relations to find the fundamental equation, uh, because if we look at this, so P is U by V, and T is square root P by B. So it is going to be square root of U by VB. So two intensive quantities are given. So two equations of state are given. For the temperature and pressure. And from the discussion that we just had in the previous problem, indeed, so if two equations of state are given, the third equation of state can be obtained. It is fixed, it is forced on us by the Gibbs-Duhem relation. So it says that the third equation of state can be obtained from this knowledge. So once we have the three equations of state, then the fundamental equation can also be obtained. So in principle, so this follows from Gibbs-Duhem relation, and so in principle we can find the equation. We can find the fundamental equation of the system. So so the reason I am dwelling on this is that this is I mean the question is a valid question, and in principle we can find uh, the fundamental equation from this given information. Yeah, so now uh, the work remaining is to actually find uh, I mean to do this and find the uh, uh, find the fundamental equation. So yeah, so we are going to uh, yeah, we are going to actually use uh, uh, these equations, of course. So P is U by V and T is square root of U by VB. So we can write these in terms of the intensive per particle quantities. So little u and little v. So P is little u by little v and T is square root little u by little v times B. Yeah, so we have to in this case we can actually use the energy differential. So let's say, so we have du is, so we have this okay, so let me start with this function u s, which is a function of s, v and n. So we can make use of the fact that it is extensive and get to this little u, right? So u of s by n, v by n and 1 is 1 by n times u of svn. So this is nothing but the little u, which is the internal energy per particle. So it's of course only a function of little s and little v. So there is no function of two variables, and we can write the differential for this. It's going to be du by ds times del u by del s times ds little s plus del little v by del little s. Yeah, sorry, del little u by del little v times dv. So this is at constant little v, this is at constant little s. So this thing now is this is clearly this is a ratio of, or sorry, this is a derivative of this intensive quantity with respect to another intensive quantity. So this is going to be intensive. So we can also write this as del capital U by del capital S at constant V and N. So we know that this is nothing but temperature. So this quantity here is also temperature. And similarly, del U by del V at constant S is going to be so which is minus p. Yeah, so we have this very useful relation that relates these intensive per particle quantities, which is d little u is t d little s minus p d little v, or another equivalent way of writing this is ds is 1 by t d little u plus p by t d little v. Yeah, so this is a differential equation, and the reason uh, for deriving this is that, so notice we have p and t given to us in terms of little u and little v, so we can make use of this this equation to finally uh, write ds as a differential of something. Let's see. So um, so p is u by v, and let us write this. 1 over t is bv by u, square root bv by u, and p by t is going to be square root bu by v. Yeah, so ds is going to be square root b times v by u square root du plus square root u by v dv. So on the left side we have an exact differential, it is ds, it is an exact differential, so the right hand side also has to be 1. So this is nothing but d of square root u times v uh, multiplied by 2. Yeah, so this gives a factor of half, so to compensate for that we have this 2 here. Yeah, that is fine. Yeah, so the right hand side is of course also an exact differential, and we can simply integrate this to get or let me this is little s. Yeah, I'm sorry if this looks big. Yeah, so this is the equation of state. This is the fundamental equation. Of course there is this lingering constant of integration which cannot be obtained from thermodynamic considerations, so we need statistical mechanics to fix this factor, but still up to this constant c we have been able to obtain the fundamental equation. So this problem is an example where we found the uh, the uh, the fundamental equation given a couple of equations of state. So these two equations of state are indeed sufficient to find the fundamental equation because of the reasons we discussed, uh, because only two intensive quantities are independent, uh, or only two equations of state are independent, and the third can be obtained from the knowledge of these two, and that means in principle we can find the equation of we can find the fundamental equation. So let me see how we're doing with time. Yeah, okay. Yeah, so now let us quickly recap thermodynamic potentials, some of the thermodynamic potentials, and how we can do Legendre transformations um, to get one from another. So let us start with this internal energy U, which is a function of S, V and N. So this is useful for describing isolated systems, so for which the internal energy is a constant, it's fixed. Isolated systems with fixed V and N, so the volume and the number of particles is fixed. So naturally the variables uh, for this function are the variables on which this function depends are S, V and N. So this is the total energy. Now we can define the free energy. This is called the Helmholtz free energy. Helmholtz free energy. Helmholtz. So here we want the system to be in contact with the thermal bath at temperature T. So this is not an isolated system. It is connected to or it is in contact with the thermal bath. And V and N are fixed. So we would like to have this some potential or some free energy, which is a function of T, V and N. So we would have to swap this variable S for T. So we have this for the internal energy, and keeping this in mind, we can derive we can define various thermodynamic potentials. So dF is sorry. So we have to get rid of this ds here. So we can see that if we define F to be U minus Ts, then this this dependence on S formally goes away. So dF will be then du minus tds minus sdt. So this first term here cancels, giving us minus pdv plus mu dn minus sdt. So like we wanted, this is a function of t, v and n formally, so it only depends on T, V and N. So this is the Helmholtz free energy. So this is the Legendre transformation that we did, where we swapped or exchanged S for T. Yeah, so similarly, let us look at another free energy. So this is the Gibbs free energy. So this is used when we have a system uh, in contact with a thermal bath, at temperature T, and it is also in contact with you can say a pressure bath. So it is so the volume of the system is not fixed. So the surrounding or the surroundings, the uh, uh, the environment that is at a, so this exerts a pressure P on the system. So for example, if we let a liquid in a beaker or a container, let it sit uh, on a table, and it is, let's say, uh, exposed to the air, then that is a system that would be described by uh, this sort of a condition. So it is in contact with the thermal bath, which is the room, the air in the room, and also the pressure uh, from the air. The air exerts the pressure on the water, on the water surface. So that would be an example of such a system. So anyway, so now of course we still want to keep the number of particles fixed. So rather than a liquid, maybe practically a solid that is just sitting in the air is a better example, because we also want the number of particles to remain constant, so it cannot exchange particles with the surroundings. uh, so we want this G to be a function of T, P and N. So we have to get rid of uh, two extensive uh, quantities starting from U. So if you start from U, okay, let me just write it like this. So U of S, V and N. So we have to do a Legendre transformation such that you swap S for T and P for V. So it should be U minus Ts. So this gets rid of S like we saw before, but now we have to get rid of V as well. So that will involve adding this term like PV. So then dg will be or this is also F plus PV, and we would get uh, this expression for the differential of G. So we have swapped two extensive variables for intensive variables here to get the Gibbs potential or the Gibbs free energy. So let us discuss one more example before doing a problem, a fun problem. Uh, so uh, so we started with U and got to uh, got to uh, this F, which is a function of TV and N. So we swapped one extensive for an intensive variable, and here in the Gibbs potential, in the Gibbs free energy, we swapped two extensive variables for two intensive variables. So here we want to describe or we want to come up with a potential that will be useful to describe systems with constant temperature, or yeah, so let me say it is in contact with thermal bath, and a particle reservoir or a particle bath at chemical potential mu. So this could be some source of particles, like a very large source of particles that can give or take particles from your system. So the number of particles is not conserved. It's not a fixed number, but the volume is fixed. So we want to have a function. So this is called the grand canonical potential, the function of T, V, and mu. So in this so we should swap S for T, starting from the internal, comparing with the internal energy. So we have to do a Legendre transformation such that S will be swapped for T and N will be swapped for mu. So we can do something like phi is F minus mu n. F is the Helmholtz free energy. So you can then see that it is only a function of TV and mu. Yeah, actually, check. Yeah, anyway, sorry. So yeah, sorry about that. So yeah, anyway, so we have this as the grand canonical potential. If you do this Legendre transformation, so this is u minus ts minus mu n. This is now a function of only TV and mu, and we can use this to describe systems where particle number is not conserved, it's not fixed. So the system can exchange both heat and particles with the environment, but the volume is fixed. So finally, let us try to see an example where we try to construct yeah. So now this coming to this question, so can you define a thermodynamic potential that has T, P and mu as the natural variables? So the question is, so let's say we start with this energy, internal energy, which is a function of S, V and N. So can you swap S for T, V for P and N for mu? Can you do this? So let's say we define some potential, something y of T, P and mu. Does it make sense to define this? And if not, why? What is it? What is the reason? So can you swap all extensive variables for intensive variables? That is the question basically. Yeah. So if you think about it, uh, does it make sense to define a system, or is it sufficient to define a system by only specifying the intensive variables? And the answer is no. Uh, so like we discussed, we can scale the system by some size, then the intensive variables will not change. So there is not complete information given when we specify the only the intensive variables. So there is not enough information. So we need at least one extensive quantity. Okay, so this can also be understood uh, based on the discussion that we did previously. So specifying three intensive variables will be overkill, or in other words, T, P and mu are not all independent. So it does not make sense to specify all these three simultaneously, or we cannot arrange for such an environment where we can independently control all T, P and mu. So all T, P, mu cannot be independently controlled. So there is no such environment in which you can tweak all these three quantities independently. Uh, but of course you can still define a function like this, but let's see how that fails. So if you define y as u minus ts plus pv minus mu n, then dy is going to be minus s dt plus v dp plus minus n d mu. Yeah, but there is nothing to celebrate here because this is simply 0. This is nothing but the Gibbs-Duhem relation. So just because of the reasons that we discussed, that you need at least one extensive quantity, or all these three cannot be independently varied. Uh, we cannot define such a thermodynamic potential, and yeah, and if you do like Legendre transformation to construct a function only of these three variables T, P and mu, yeah, it is just a trivial, it is trivial because of the Gibbs-Duhem relation, uh, or because of the fact that we have uh, some relation between these three quantities. Yeah, so yeah, okay, so I guess that is it for today. So yeah, okay, next week I think we'll discuss some problems on Maxwell's relations and their applications. Okay, then bye.